Hello. Good afternoon. I'm David Heilbron. I'm a member of this congregation. Before I introduce our speaker, Professor Andrew Fraknoi, I would like to mention three other things. First, we would like to thank David Jones and Donald Williams for the cake they donated in honor of their 40th anniversary. Would you please stand up? Are David and Doug here? Okay, all right. Second, the cake, that cake. Second, Reverend John Buren's book about the Transcendentalist Conflagration is for sale right over there in the corner. And thirdly, I would like to present some background about Darwin Day and the humanist role in it. The mission of the International Darwin Day is to inspire people throughout the globe to reflect and act on the principles of intellectual bravery, perpetual curiosity, scientific thinking, and hunger for the truth, as embodied in Charles Darwin. Yay! Ever since he published his radically insightful book, The Origin of Species, in 1859, Darwin has been the focus of commemorations throughout the world. The organized movement to have an annual International Darwin Day celebration began in 1995, and eventually it was incorporated in California in 2002 as the Darwin Day celebration. In anticipation of Darwin's bicentennial birthday, February 12, 2009, the Darwin Day celebration paired with the American Humanist Association to support the growth of Darwin Day activities. The Humanist Association remains the lead agency charged with amplifying the International Darwin Day Foundation's mission. Our speaker today, Professor Andrew Fraknoi, retired in 2012 from Foothill College. He was the California Professor of the Year in 2007. He now teaches astronomy courses to senior citizens at the Fromm Institute, University of San Francisco, and at the Osher Lifelong Institute at San Francisco State. A number of us have attended his courses there. He served as executive director of the Astronomical Society of the Pacific for 14 years. The International Astronomical Unit has named asteroid number 4859 as Asteroid Fraknoi to honor his contribution to the public understanding of science. Here we have the title of Professor Fraknoi's talk, What Were the Atoms in Your Body Doing 8 Billion Years Ago? Cosmic Evolution. It's my pleasure to present Professor and yes. That was a good one. Present Professor Andrew Fraknoi.
Great. Thank you so much for that introduction. And I want to reassure those of you who don't know about asteroid Fraknoi that it's a very boring asteroid in the main belt of asteroids and no danger to the Earth at all. So, as you heard, my pleasure and task today is to answer the question that I know has been keeping all of you up at night. What were the atoms in your body doing 8 billion years ago? And to talk more broadly about evolution. Let me wish all of you the happy Darwin Day that you heard about. But Darwin only went so far. Darwin talked about evolution, the slow changes to life on Earth, and we now know that evolution on Earth is only a tiny part of a much larger process of evolution in the universe. It turns out that like life on Earth, over many, many, many centuries, millennia, and even longer spans of time, the universe underwent small changes and developed in ways that made a creature as interesting as you possible. And that's what I want to talk about today. I also want to answer Lucy's question here. And I'm going to tell you what the stars did for you. By the end of this discussion, you'll know all about that. Well, let's take a quick tour of the universe for those of you who are not students of mine. Let's just briefly introduce what's out there so we can then talk about it. Astronomers generally divide the realm beyond the Earth's atmosphere into three different categories. The first is realm one, what we might call our neighborhood, the solar system, the sun, and its family, and you are living on one member of the solar system, planet Earth. But there are other members as well, and here they are to scale. You see the sun, the star that is the center of our solar system, to scale with the planets. And this is an old slide, so Pluto still counts as a planet, in case you were upset about that. And you can see that most of the planets, well, I would say all of the planets, and maybe all of the planets together, would fit into that red eruption on the right side of the slide from the sun. And you can see on this slide that 12 Earths could fit side by side into the diameter of the giant planet Jupiter. So if anyone came into this discussion with an exaggerated sense of his or her importance, slides like this are good for you. We recommend it particularly for people in Washington and Sacramento. You can see that we are a very small part, even of this local neighborhood. But I want to go beyond that today. I want to talk about realm two as well, which is the galaxy, the Milky Way galaxy, our city of stars, our collection of stars, in which the sun is one of perhaps 400 billion stars. Here you see a few of them. And you can see that with a telescope, we can see stars far better than you can see with the naked eye, especially from San Francisco. And you can see just bazillions and bazillions of stars, some of them on the foreground and quite blue, and others in the background and so dim that their light doesn't even activate your color vision. When it's very dim, you don't see color, you just see black and white. And there are stars everywhere we look within the Milky Way galaxy. Not only stars, but also raw material. It's like driving in San Francisco. Wherever you are, they're not finished, right? There's construction going on. And the same is true in the galaxy. There's still a humongous amount of cosmic raw material, gas and dust, out of which new stars, new planets, and perhaps even new Unitarians are being made at this moment, right? So this is a very beautiful example of a cloud of reddish gas, literally gas of the kind that we're breathing right now, individual atoms and molecules. And it's out of this storehouse of raw material that new construction is going on, that new stars are being made even today. So the entire Milky Way galaxy makes up a kind of flat disk or pinwheel. This is not a picture. We don't have a good picture of the Milky Way galaxy because we're in it. It's like trying to take a picture of yourself from inside your kneecap. The view is not very good. But we are there where the yellow sun is shown, and there are these great spiral arms of stars going off for enormous distances. And then the third realm is the universe. And this is a relatively recent discovery in human thought. that in addition to this enormous Milky Way galaxy of which we are part, there are many other galaxies. In fact, galaxy after galaxy after galaxy has been found. Some look like our Milky Way. This is what we would look like if you could look down on us from above, a beautiful pinwheel of hundreds of billions of stars merging their light together. And not only do stars congregate in galaxies, galaxies congregate in groups. Here's a beautiful group of galaxies captured by the Hubble Space Telescope. And so we see enormous numbers of galaxies, each containing enormous numbers of stars as far as our telescope will allow us. And now I want to get to a very important point for this discussion, which is the only way that we know about distant galaxies or even stars in our own galaxy is by their light. We can't go there. We haven't sent probes anywhere except our own solar system. So everything we know about the universe out there, we get from light traveling to us. And that light travels at a speed, which we call the speed of light. And the speed of light is a finite speed. It's 670 million miles per hour, in case you're writing things down, which is a lot faster than you should be going on your way home. 670 million miles per hour. It's very fast, but it's finite. And that means that light takes a while to get to us at that speed. We use a unit called the light year, which is just simply the number of years that the light takes to get to us at the speed of light. So if something is 100 light years away, that means the light takes 100 years to cross the vast gulf of cosmic space between us and them. If something is 1,000 light years away, light takes 1,000 years, and so on. And there's an immediate consequence to this, which is very deep if you really think about it, which is that the further out we look, the longer ago we are seeing. Say that again. So since light takes a while to get here, the further away something is, the longer the light takes to get to us. We see galaxies, like on this slide taken by the Hubble, galaxies that are 10 billion light years away, which means the light we see tonight left those galaxies 10 billion years ago when the sun and the earth didn't exist. So the further out we look, the longer ago we are seeing, and this means that we have the ability to reconstruct the history of the universe. This is what makes astronomy so amazing in the 20th century. By being able to look so far out, we're able to look far enough back so that I can actually stand here and tell you what happened in the universe billions of years ago. And we can talk about cosmic evolution. That's the key to my having the nerve to give this lecture. And I want to finish our introduction with one more slide. This is a galaxy of stars. And in this galaxy of stars, which looks like a fuzzy blob here, sort of cigar-shaped, there is a brilliant point of light. That brilliant point of light was seen in 2014. And that point of light got to be bigger than all the stars in the galaxy. I'm sorry, got to be brighter than all the stars in the galaxy put together. And that's not right. One point of light in that galaxy got to be brighter than all the stars that make up that galaxy. That shouldn't be legal, but it was. And that kind of brightening is the key to the story I want to tell you today. Now, after a quick tour like this, you're probably ready to agree with Charlie Brown. So, I want to now ask you a personal question. Could you look at your hand for me? And tell me, please, what atoms your hand is made of. I will take nominations from the floor. What atoms are in your hand? Hydrogen. Carbon. Oxygen. Nitrogen. Iron for your tired blood. Calcium in your bones. Phosphorus. Copper. Sodium and chlorine, right, which make up salt, and so on. So there are a lot of interesting atoms in your hand. And what's interesting for astronomers is that we can use the light to actually fingerprint the stars. We can take white light, pass it through a prism, make it into a rainbow, and it turns out there are clues when you look carefully at the light from the stars. There are lines in the spectrum, specific colors in the spectrum, which are unique to each element. And so we can actually fingerprint the stars. We can tell which elements are present in the stars. Hydrogen has one pattern, which you see below the rainbow. Helium, another pattern. Mercury, another pattern. It's very much like the barcodes you see at Safeway, right? Each different product has a different barcode. Each different element leaves different colors of light. And if you can separate the colors well with very precise instruments, you can actually learn what elements are in the stars. And here's where one of the great discoveries of astronomy comes in. The further out we look, the simpler the universe gets. Say that again. So the further back we look in time, the more the universe seems to be made of very simple elements. And when we look back to the beginning, when we fingerprint the galaxies and the stars 10 billion, 11 billion, 12 billion light years away, when we look at the earliest light we can possibly see, everything is made of just two elements, hydrogen and helium, which are the simplest, cheapest elements in the universe. They're made of the simplest constituents. Here is hydrogen. It consists of one proton and one electron. Hydrogen is so poor it can't even afford a neutron. This is the simplest element, and the vast majority of the universe is made up of hydrogen. And when we look really far back, it's all hydrogen and a little bit of element number 2 with 2 protons called helium. So, as Harlan Ellison, the science fiction writer, wrote, the 2 most common elements in the universe are now known to be hydrogen and stupidity. This is not a political comment, but it could be, especially these days. So, where the heck did all the other elements come from? If, as we now firmly believe, the Big Bang began with just hydrogen and made a little bit of helium in the process of banging that Big Bang, where the heck did all the other elements that we take for granted on Earth come from? They had to be made. The universe had to evolve to make those elements. And that is one important key to the topic of cosmic evolution. If the Earth had come along 12 billion years ago, it would be made only of gas. There would be no land to stand on. And certainly life as we know it would not be possible because the elements required, carbon and all the other ones you listed, would not yet be available in the universe. So the real question is, where did the elements come from? Well, they had to somehow be made from hydrogen and helium. Well, this, ladies and gentlemen, is alchemy. Isn't that what the alchemists wanted to do in the Middle Ages? They wanted to take one element, one fundamental substance, and turn it into another element, a different fundamental substance, hopefully a cheap one into an expensive one so they could make money. So how did the alchemists do in the Middle Ages? Not so good. Not one of those experiments ever really transformed or transmuted the elements. And we now know why. We are fully aware the reason that the alchemists never made a new element on Earth is because the minimum temperature required, are you ready for this? The minimum temperature required to change even the simplest element, hydrogen, into something more complicated is 10 million degrees. 10 million degrees. And if an alchemist had gotten his or her oven that hot, it would have melted the neighborhood and been very embarrassing for everyone concerned. So in fact, on Earth, we cannot in any natural way, now we can do this in atom smashers, but in a natural way, elements are not transmuted. Changes happen chemically, molecules form and substances break up into simpler parts. But new elements cannot be created naturally on Earth because the temperature is too low. The only place in the universe where this can happen naturally is inside stars. Deep inside every star, the pressure and the temperature are so high that in fact new elements can be made in that star. We now know that stars like the sun, which you see pictured here, in fact shine because of the energy released in the making of new elements. This is a wonderfully good sort of hand-in-hand process. Not only are the stars able to make new elements, but the process of making them actually produces extra energy, which comes out as starshine. How wonderful that nature managed this two-for-one deal. So in fact, we now know that inside the sun and every other star, new elements are made. At first, hydrogen is transmuted into helium, element number 2, but that's not a big deal. But then every star, at some point in its life, transforms helium into the next element that happens to be easiest to make, and that's carbon. So every star at its center will make carbon out of helium at some point in its life. And that's where the carbon in your hand came from. It wasn't in the universe to begin with, it was manufactured inside stars. Now, some stars, the biggest stars, the most massive stars, the ones that have the most gravity and can squeeze because of gravity, their center is hot enough, actually go on and make other elements. They turn carbon into oxygen. Take a deep breath. All the oxygen that enters your lungs was once made inside a massive star. Beyond oxygen, we make silicon, for example. All the silicon in the sand that you enjoy on the beach is made inside these massive stars. So it is stars that make the new elements. And the question is, if stars were made inside of elements, how did they get into you? And the answer turns out to be stars die. Stars are not forever, even they look like they're always around. That's only human timescales. Stars over the longest timescale die. Some stars die peacefully. For example, the sun. Our sun will, at the end of its life, just kind of collapse, say, oh, I can't take it anymore. You know that feeling. And it's just going to collapse until it's almost solidified. It'll be super hot, so it won't be a regular solid, but it'll have some of the properties of a solid. It'll be, if I can use the technical word, very squozen. It'll be very densely compressed. But that's not the story I want to tell you today. Our sun will die a peaceful death, and that's fine. That's not going to release any elements. But the more massive stars, the big, heavy-duty stars, turn out to have a different death in store. Stars that are really massive, at the end of their lives, become unstable, and they actually explode. They explode, they blow themselves to smithereens. It's very nice. Nature always puts an arrow there just before the start. No, we put the arrow. But there you see a nondescript star that you wouldn't have noticed except for the arrow. And in 1987, February 1987, that star suddenly started looking like the right-hand side of the slide. It started to explode, and it became brilliant. Even though it was 160,000 light years away, it was bright enough, it was noticeable by the human eye without a telescope. It was, unfortunately, it was only noticeable in the southern hemisphere, so that's why you probably didn't hear about it in 1987. But we astronomers heard about it a lot. So some stars, as I say, at the end of their lives, explode. And we actually knew this from historical records. Those who study sort of the cave art in the Americas and records left in some parts of Europe, but particularly records left in Asia, in China in particular, know that in July of 1054, a little before our time, but in 1054, a star became so bright that it was actually visible in the daytime. The Chinese called it a guest star because it was a guest of the emperor. Anybody who intruded had to be a guest of the emperor and get permission. So this guest star was actually visible during the daytime. It knocked people's socks off. They didn't wear socks, but never mind. And in fact, it stayed bright for weeks in the daytime sky. Today, this is what the object, I should say, the Chinese astronomers kept such good track of exactly where the guest star was relative to other stars that we can point a telescope there today, precisely to the location they left us from 1,000 years ago. And here's what it looks like today. A mess. But doesn't that look like something that exploded? It's called the Crab Nebula because if you squint your eyes, it sort of looks like the shell of a crab, but I don't see much of a crab there. But what I see is very, very clear evidence of cosmic violence. All you have are the filaments, the shreds of what was once a star that blew itself into pieces, blew itself into atoms. It's not the only such guest star that we observed. In 1006, there was another star, even brighter. That was the brightest exploding star we'd ever seen. Now, people didn't know what they were looking at that time. And then there was another not quite so bright one in 1572. This is a woodcut from that time. People went out and looked at that star. They called it a new star because the star that exploded was too dim to be seen with the naked eye. And when it exploded, it came brilliantly bright, and so it looked like a new star had appeared in the heavens. In Latin, that would be nova. We have a PBS series with that name, Nova. Now, there are other stars that brighten up for more sort of ordinary reasons. So pretty soon we wanted to distinguish the more ordinary brightening stars called nova and these really dramatic brightening stars. So we started calling them supernova. Anything that's super is like top of the heap, right? Superman is the greatest superhero and so on. So these are now called a supernova or supernovae. As I say, we saw one in 1572. Then Kepler saw another one in 1604. That was pretty close for two stars to explode so close together. And in 1610, Galileo perfected the telescope. So we could have looked at them, but it was too late. They were already faded away. 1572, 1604, and we haven't had one in the neighborhood since. After we invented the telescope, the sky got shy, and no other star has exploded. And this is incredibly frustrating to astronomers, because finally we have a telescope. Why doesn't one explode close by? So as I say, one did explode in 1987 in the next galaxy, in the next little cloud of stars, 160,000 light years away. And we've been observing that furiously ever since. But we sure would like something to explode. Maybe not too close, but something to explode so that we can now observe it with the newfangled instrument called the telescope. So this is the gist of my story about sort of the evolution of the universe. But now let's look at the evolutionary processes in a little more detail. So as I say, elements are made in stars. When stars explode, they recycle these elements. As I like to say, particularly in a church, the supernova giveth and the supernova taketh away. And I want to talk about both those issues briefly. First, as I've hinted, the supernova is what recycles the element. Every time one of these stars blows up, all the elements that it made, carbon, oxygen, silicon, all the ones that are essential for life and for the Earth itself, are thrown into space at great speed, where they then join the material that's already there, the raw material that I showed you. It's out of that raw material that new stars, new planets are formed, and now that raw material is enriched by what the exploding star donated, recycled into those clouds of raw material. So when the next system of star and planets forms, it will have not just hydrogen and helium, but a little bit of carbon and oxygen and silicon and all those elements. And then new stars form. Some of them will die peacefully. Others will make new elements and explode. And their newly formed elements will be recycled into the next cloud that happens to make a star. So generation by generation, we enrich the material of the universe with additional heavier elements, with more and more of the stuff you need to build a Unitarian. So that's great. That means that as time goes on, the universe becomes more ready to make you. We, the sun and the earth, were born 4.6 billion years ago when a new star called the sun formed out of a cloud of cosmic raw material. 4.6 billion years ago, when the earth formed, a whole bunch of exploding stars had gone off in the neighborhood in all the years before, so we formed from well-enriched stuff. Still, if you look at the sun, it's 99% hydrogen and helium, but that 1% represents a lot of other stuff like carbon, oxygen, etc. And the Earth, which lost its gas early on, consists mostly of heavier elements, although we have hydrogen in the water, of course, and in other molecules. So we formed from enriched stuff, and there was enough of these complicated atoms to make something as interesting as you. So, as my romantic students like to say, we are made of stardust. Every atom in your hand that wasn't hydrogen or helium, you don't have too much helium, all the atoms in your hand that aren't hydrogen were made for you by previous generations of stars that gave their lives so you could have these atoms and incorporate them into your own body. And these atoms are on loan to you from the great lending library of atoms in the universe for the period of your life. Then when you are recycled, you will then donate them back to the reservoir of atoms on Earth, and perhaps someday new creatures will be formed from the atoms that you are now borrowing from the universe. We are all made of stardust. That's what the romantic students say. The cynics among my students say, so professor, what you're really saying is that we're the recycled garbage of stars, right? And that's true too, if you want to look at it that way. Every human being, whatever race, color, or creed we are, is made up of the atoms formed by stars. But there's a problem. Turns out that when stars go unstable, when they're ready to explode, the heaviest element they've made is iron. Iron turns out to be the heaviest element that a regular star can make during its life. And when it makes iron, that's when it becomes unstable for complicated reasons, and the star explodes. Now, there are a lot of elements heavier than iron, and some of them are quite dear to you. Anybody know what those are? Silver, gold, and platinum. Jewelry. So we like to call this the jewelry problem. If the stars stop making elements when they explode with iron, where the heck did your jewelry come from? And if you can't answer the question, are you still allowed to keep it? Where did the gold, the silver, the platinum, all the heavier elements, lead, uranium, many things we really need for civilization as we know it, where did they come from? And it took us a few more years to figure that out, but we now have figured it out. The heavier elements come from the explosion itself. When the star explodes, the instability that leads to the explosion is so violent, so chaotic, that in that enormous outthrowing, is that a word? In the out-movement of the materials, so much collision and so much energy takes place and involves these atoms that heavier atoms can be made in the explosion itself. So we believe that gold, silver, and platinum was made not by the peaceful life of stars, but in the violent death of stars, in the supernova itself. So when one of your kids or grandkids is ready to give a gold band to his or her sweetheart, make sure they mention this gold band was forged in an exploding star. That's how much I think of you. I'm giving you pieces of an exploding star as part of this marriage contract. So that's great, and that explains. By the way, I have to say, because there might be astronomy nerds in the audience, for a long time, that was the discussion. Jewelry was all made by exploding stars. Today we know better. There's actually a second process that also makes some of the gold and silver and the heavier elements, and that's the collision of two star corpses. This is beyond the level of this discussion, but these stars leave behind a corpse, a little squozen piece of stuff after the explosion. They're called neutron stars. And if two neutron stars collide, they explode again, and they can make some of the heavier elements too. So we've actually just recently seen gravity waves. Einstein predicted that gravity disturbances would also create very, very faint waves. We've never been able to pick those up, but in the last few years we've picked them up. The Nobel Prize was given for that, and we picked up actual gravity waves from these star corpses colliding, and we know that they're also making gold. So it's not just these explosions, but it's still a good story. It's just not the complete story. But there's more. For only $3.99, there's more. It turns out that supernovae, exploding stars, have two more services that they provide for us that many people don't know about. One has to do with making new stars. Why some Thursday does a particular blob of material sitting out there as raw material, having been sitting out there for millions of years, why some Thursday does it decide, okay, today's the day to make a new star. I'm going to start collapsing and make a new star in some planets and see what happens. What causes new stars to suddenly form? And we think when there are cosmic raw material bubbles like that, it needs to get a little push from somewhere. Some kind of shock, some kind of push has to pass over that cloud of raw material to get it started to collapse down to make stars. What in the universe could give a push to a peacefully minding its own business cloud of raw material? Well, what if there were an explosion nearby? That explosion would then give a push to the peacefully sitting cloud. The supernova would compress with its shock of energy the cloud and make a new system of stars. And there you see a kind of arc of stars, which we think was made by an exploding star many years before. So we think that the story not only is that the elements come from these supernovae, but one generation of supernovae might be the shock that gets the next generation of stars started. I think that's very romantic. The first generation of stars dies, but it gives its life so the next generation can begin. That's very nice. But there's one more, which is not so sure. This is still hotly debated among scientists. But if you ask people who are interested in evolution, if you ask people who are Darwinians, should we be here already? Should we humans be here, or should we have already evolved? Many people who are experts in the field say, no, we shouldn't be here yet. Now, what do they mean by that? Turns out that evolution on Earth proceeds by small, subtle changes to your DNA. Your DNA are the instructions for making a copy of you, a copy of your cells in your systems. And every once in a while, the instructions go wrong. You know this from having assembled IKEA furniture, right? Every once in a while, instructions go wrong. And so it can be that something zaps the blueprint, that is your DNA, and the copy isn't exactly like the original. We call those mutations. So what causes, and mutations is what leads to change in evolution and makes up ultimately evolution. Many of these mutations are not good for organisms and the creatures die out, but some just turn out to be a little bit better, a little bit easier for survival, and those mutations are then passed on to the next generation and are incorporated into the blueprint for that creature. What determines the number of these mutations? Well, something has to, I'm going to use a technical term again, something has to zap your DNA. What do I mean by zap? I mean either some large amount of energy or a fast-moving particle has to hit the DNA so that this change at the atomic level occurs to your DNA blueprint. The cause for those mutations can be energy from inside the Earth. We have a lot of radioactive rocks inside the Earth, and they send energy outward, which could cause mutations. That's why people who work in nuclear power plants that go bad turn out to have so many mutations, they get cancer. And in the same way, just like the ground radioactivity can produce mutations, radioactivity or high energy from the sky can produce mutations. We have figured out the level of mutation-causing radiation that the Earth normally has. Just from the rocks and from our environment and from the sun, what's the typical level? And if the typical level were what caused evolution, we should not yet have evolved. We should be much simpler creatures just from the rate of mutation that the Earth and the sun provide. Something in the history of the Earth caused increased periods of mutation and speeded up evolution beyond the regular baseline level. Well, what could have produced a lot of high-energy particles from the sky? Supernova explosions. Over the 4.6 billion years that the Earth has been around and the 3.5 billion years that evolution has been going on, stars have exploded near enough to us that the radiation, the particles, and the energy from the explosion have come here, and they may have briefly speeded up evolution sufficiently to cause the extra rate of mutation and the faster evolution that made you being here today possible. So another thing we can thank supernovae for. We believe that nearby supernova explosions can increase the rate of mutations and speed up evolution on Earth. As I say, that's not totally established, but it looks good enough that we're actually starting to put it in the textbook. So it's pretty reasonable. So you might therefore agree with my bumper sticker. But I want to finish this little discussion by just reminding you that there are two sides to every story, and supernova can also be very dangerous. If a massive star explodes too close to us, then it could wipe away, for example, something like the ozone layer of the Earth, or if it's close enough, the atmosphere of the Earth could be just kind of propelled out into space, which would be hard on children and growing things if we lost our atmosphere. So if you're too close to a supernova, it could actually not just harm, but perhaps destroy all life on Earth. How close do you have to be? People are still debating, but roughly 30 light years. So the number one question you probably would have for me if I didn't answer it, Professor Fraknoi, are there any massive stars within 30 light years of the Earth getting ready to explode? Do I need to put an extra rider on my insurance policy? And the answer, I'm happy to report, is no. There's no star anywhere within the distance, even in the most remote possibility of how we could be harmed. No massive star is near enough to us to be a source of danger today. Now, come back in a million years and we'll talk. But right now, there's no star ready to threaten us. But that's just because we happen to pick real estate that's good. You know what it is about real estate: location, location, location. We happen to be in a peaceful location. But you could imagine some other star system in which their caveman goes up and says, "Starlight, star bright, first supernova I see tonight," and that may be the last thing they think about. And more seriously, it could be that around the galaxy, other intelligent life forms sufficiently intelligent to have Unitarian assemblages. Really nice life forms have developed, but they had the bad luck of living on around a star whose neighbor star got ready to explode, and through no fault of this particular species or this particular planet, that nearby supernova explosion wiped them off the face of history in the galaxy. So we should be grateful that we're not near one of these exploding stars, but we should perhaps give a thought to what might have been a number of intelligent species that were wiped out over the history of the galaxy. So supernovae can do good things, they can do bad things, but they are a key to the evolution of life in the universe, and therefore to the evolution of the universe itself, if you regard life as being an important component of the universe. So I hope in this short introduction I've been able to show you that in fact evolution doesn't just concern Earth and people and the creatures we love, but a much larger question of how the universe changes. As the universe continues to evolve, it will have more and more heavy elements contributed by supernovae, make more planets full of heavy elements, and be ready to make new life forms and perhaps even new intelligent civilizations. It's very possible, in fact, we hope, that we are not the most intelligent civilization in the universe, that even it would be a terrible thing if we were in some ways, but that there are already older, more advanced civilizations that perhaps deal with their planet and each other more wisely. And if the universe continues to evolve, maybe our hope can be that wiser creatures than us evolve in many different places. You saw your hand, and your hand is a wonderful example in the way that we and the universe have evolved together. Thank you very much.
So Professor Fraknoi has agreed to answer questions. So if you have a question, lift your hand up and I'll bring you the microphone.
So just before you spoke, I was reading an article that Betelgeuse is diminishing in its brightness and might be approaching a supernova. Can you comment on that?
Oh, this is great. So somebody's very well informed about the news in the front row. That's great. So there is a massive star, which you perhaps know if you're a stargazer, in the constellation of Orion, called Betelgeuse. Some people say Betelgeuse, but Betelgeuse is good enough. That's how most people pronounce it. And it is, in fact, a star which is well along in its life. It's far enough away we don't have to worry about it, 600 light years away. But this star is actually showing some signs of instability. Now, it turns out it's been showing it for hundreds of years. It's not just today. But, of course, we notice everything more today, and because of social media, it gets around more. So recently, there have been a spate of articles. Betelgeuse is going unstable. Is it going to explode? And the answer is probably not. It's been unstable for hundreds of years. It's still in that part of its life where it's just having its ups and downs. We all know as we get older, we have these days when we have our ups and downs. It's not yet in the stage where it's going to be ready to explode. Someday, probably not in our lifetime, but someday Betelgeuse might well explode and become a bright star in the daytime or the evening sky. But it's just unstable. It's not yet ready to explode.
Dr. Fraknoi, thank you for your presentation. In our galaxy, most of the stars are red dwarfs and sun-like stars that are never going to explode. How many solar masses does a star need to have to explode, and what percentage of our galaxy are those stars?
Yeah, great question. So turns out that the galaxy is similar to Hollywood, right? Hollywood has a lot of dim stars and not that many superstars, right? Many of the actors in Hollywood are still making their money waiting on tables in delis in Los Angeles, right? So in the same way, the vast majority, as you say, of stars are dim and low-mass stars, which are the ones that collapse. So we are trying to figure out, the answer to your question, exactly what percentage of stars are the ones that explode, and how big do you have to be to explode? And the reason I can't answer that with just a simple number is that as stars get older, they lose some of their material. This is called the Jenny Craig effect. They lose some of their mass. Material gets unstable toward the end. Stars expand and contract and expand and contract. They lose some of their material. So how much mass they start with is not what's important. It's how much mass they are, how big a mass they have when they are ready to die. And so we think that stars typically today that have 8 to 10 times the mass of the sun are the ones that are going to explode. But what you need to not collapse, but to go through the future stages, is for your center, for the part where the nuclear fusion is going on, to have more than 1.4 times the mass of the sun. So the core has to be greater than 1.4 times the mass of the sun to cause the next kinds of cataclysmic events. All right.
You were talking about when you have a supernova, suddenly it becomes bright in the sky and it's visible for us down here. How long is it in that bright state before it, how quickly does that happen?
Great. So how long does a supernova stay bright? Depends on the supernova, but certainly weeks. If one were to go off and become visible to the naked eye, it would be weeks. Sometimes it's a little more, depending on exactly. There are several types of supernovae. Everything I've told you is a little bit of a simplification, so I could present it in an hour. But yeah, certainly weeks. And I just want to say, imagine if that actually happened today, if the 1054 explosion happened today so that it became bright enough to be visible during the daytime. What would people say? Right? People would think it's a religious issue. It's a sign from God. Many people would assume that it's a nuclear missile coming our way, right? I mean, the paranoid interpretations would be everywhere. And if such a thing were to happen, if by some chance some star in our galaxy does go supernova and there's a new star in the sky, I've now deputized all of you to be the voice of reason in your community, right? So if such a thing were to happen in your lifetime and your neighbors are panicking, oh my God, it's the end of the world, you say, no, 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 no. I remember I heard this talk from the astronomer with the weird name, and he told us that it's just an exploding star. They're not close enough to hurt us. Don't worry, this is just a natural process in the galaxy. Go back to Netflix or whatever you were doing.
Thank you so much. Wonderful talk. She kind of stole my question a little bit, but so furthermore on that, has it been confirmed with like wavelength analysis that during that 2-week period, the larger molecules are created?
Great.
And then secondly, can you just comment on whether there's multiple big bangs in perpetuity or continually, or if there's just been one big bang event?
That's two questions, one of which I can answer, and the other one is beyond all human understanding, but I'll talk briefly about it. So the first question, the easy one, is, have we actually observed heavy elements like gold coming out of these explosions? This is in the category of my favorite type of question, which is, why should I believe a word of what you said? Right? I love questions like that. That's what I tell my students to ask about everything. If we only asked that about political advertising or Facebook posts, it would be such a better world. Why should I believe a word of this, right? So this is a great question. If you say gold is being made by these exploding stars, do we actually see gold coming out of the stars? And the answer is yes. Particularly the one in 1987, which, although was far away, could be observed by all kinds of telescopes around the world, 1987 vintage, not Galileo vintage telescopes. And yes, indeed, we see heavier elements coming out in large quantities, just the way the theory predicts.
When is the next pulsar?
Ooh, that's a very sophisticated question. So let's fill in the people who don't know as much as you do. When the supernova explodes, I mentioned that it leaves behind a kind of remnant, a kind of star corpse. And it's really, really squozen. The supernova explosion really takes the leftover material and squeezes it unbelievably. It's squozen so much that, in fact, more than the mass of our sun is squeezed into a ball about 20 miles across. That's really squozen. Right? And that's called a neutron star because the changes that are undergone by the material in the collapsing core are such that protons and electrons merge together and make neutrons. So this neutron star is really squozen, and then around it is an atmosphere of regular matter, which turns out to be highly magnetic. And it turns out these neutron stars, if they're spinning, can actually develop a magnetic pole, like a north and south pole, and emit radiation, emit energy from the spinning along the poles. And these, if the poles happen to be facing toward us as it spins, so the poles are not up and down, but sideways, so the north pole points toward you, and then as it spins, the south pole points toward you, and then the north pole, and then the south pole, then we can actually get pulses of energy. This is really great. In 1968, a graduate student in England who was doing extra work, Jocelyn Bell, discovered pulses of radiation like this, and they were so regular, she didn't know what to call them, so they called them pulsars, because they pulsed and pulsed and pulsed. A Japanese watch company stole the name, and you can now buy pulsar watches. And these pulsars turned out to be neutron stars, spinning neutron stars. So this was an amazing thing because we never thought we'd see those star corpses. We thought we'd see the explosions, but not the corpses. And now these pulsars show them to us. And the fourth pulsar was discovered at the center of the Crab Nebula, the explosion in 1054. So we know they're associated with the explosions of stars because there was a pulsar in the middle. So the question is, when will we see the next pulsar? Ask me when we see the next supernova, and maybe we'll make a pulsar. Not all supernova explosions make a neutron star. Not all neutron stars show up as pulsars, but that's what we have to wait for. We have to wait for a supernova explosion. Now, thousands of these pulsars have been seen, so there are a lot of star corpses already around, which confirms that there should have been a lot of explosions, which explains why there's so many heavier materials in the Earth. So it all seems to fit together nicely.
The title of your talk said, what were your atoms doing 8 billion years ago? And I was wondering why you chose 8 billion, and what were they doing then?
Great question. I should have said more about that. Thank you. Yes. So 8 billion years ago, I chose that because the Earth and the Sun formed 5 billion years ago. So that seemed long enough ago that no one could mistake your atoms already being part of this solar system. So what were your atoms doing 8 billion years ago? Well, you have a lot of atoms. So not all the atoms were doing the same thing. But certainly it's fair to say that 8 billion years ago, some of your atoms were inside a previous generation star, which then later exploded, threw those atoms out into space, and may have contributed eventually to the reservoir of heavier materials in the Earth. The Earth then produced a blade of grass, a cow ate the grass, your parents ate the cow, and I'll leave it to the biology teachers to take the next step. Here you are. I can't hear you.
Oh, sorry. I wanted to ask a question about black holes. I was looking at, I'm interested in black holes, and I was seeing this great, huge black hole they had recently discovered that was the biggest black hole ever. Would you comment on that and relate it to what we're talking about?
Thank you. I mean, I'm only sighing because I don't know how patient you guys are. That's another 1-hour lecture, which I can give some other time. No, I will answer. I will answer. But by the way, a shameless plug for those of you who are part of the Fromm Institute. Anybody can be part of it. I'm about to teach a course at USF called The Violent Universe, which will answer that question in several hours. So you'll get all the gory details in that course. But so black holes are another way that stars die. There's an even more massive group of stars which can't even explode. It's so overweight. You know how people are. They're so overweight. They have a completely different fate in store for them. And these stars just collapse until gravity overwhelms everything and warps the very nature of space and time itself. And those completely collapsed stars where not even light can emerge from the warping, those are called black holes. And as you may have heard, recently astronomers took the first picture of a black hole, which you might think is not possible because black holes are black and they're tiny when they've collapsed, and space is black, so how the heck are you going to take a picture? But it turns out black holes are hungry, like people. They like to eat quite a bit. And so black holes are often surrounded, if there's food nearby, with a whirlpool of food that they're ingesting. And we saw the shadow of the black hole against the whirlpool of food going in. And that's the picture they took. But you're quite right that we're now discovering more and more massive black holes. And some black holes have eaten as much as 2 billion suns. Black holes, they have to be in a very crowded neighborhood to have that much food, but 2 billion suns worth of food. So that's a whole nother topic, which is one of my favorites in astronomy.
My wife and her 3 kids were in Chernobyl when it blew, and for 5 days, the Russians didn't tell them about it. My wife's thyroid is gone because of that. So my question is, number one, I went to Ohio State. You know about the SETI thing in 1977. We have a radio telescope the size of a football field, and we got that actual, you know about SETI, right?
Yes.
Can you talk about that?
Sure.
Because I was just a minor in astronomy. You're an astronomer.
Okay, so this is a completely different topic. That's one of my favorites too. SETI, the search for extraterrestrial intelligence. We have so little intelligence on Earth, we're looking for it elsewhere. And I actually have the privilege of being on the board of the SETI Institute, which is one of the main organizations searching for intelligent life. And indeed, one of the ways we are searching for life elsewhere is that they may be sending some kind of message out into the universe, like a lighthouse or some kind of beacon that simply says, we're here, hello, hello, something really powerful that could go across the vast spaces between the stars. And we've looked for signals like this for ever since 1960 when Franck did the first such search. And one of the questions we have to deal with every time we do a search like that is, what do we do when we suddenly get a burst of energy, like a big radio energy burst, and then it goes away, and we never see it again? And that's what happened at Ohio State some years ago. They had a powerful radio telescope pointing, searching for unusual things. They saw a burst of energy. Somebody wrote "wow" on the printout. So ever since that's been called the wow signal, because the graduate student wrote "wow" there. It was very loud, and we never saw it again. We never got anything from that star from that direction again. We have searched and searched and searched. We've directed even better telescopes in that direction. So it probably was something natural from behind that star or around that star, but we can only declare an experiment to be a success when we can repeat it. And we are not going to declare aliens existing until we get some kind of regularly repeating message or some confirmable phenomenon. So there have been dozens of such messages, not just the most famous messages in the sense that they come from the static of the universe, but so far nothing that has given any indication of coming from alien technology. But stay tuned. As you may have heard, recently a billionaire in Silicon Valley has given $100 million to Berkeley to make the search far better than any search has ever been before. I'm actually on the advisory group for that project. It's called Breakthrough Listen. So in the next 5 or 6 years, we're going to be training all kinds of telescopes out there searching for advanced civilizations. Stay tuned. Maybe we'll find something in the next 5 or 6 years.
Thank you very much, Professor, for this fascinating talk. But the thing that you've done, unquestionably, is you've shown us how atoms might be born. My curiosity is, are they after that immortal?
Ah, great question. So do all the atoms made in this process stay around forever? And the answer is no. For example, there are atoms which by their very nature have nervous breakdowns and fall apart. We all have relatives like this, right? But what do we call atoms in nature that just completely fall apart? Radioactive atoms. Uranium, thorium, radium. These are all elements which after a while say, I can't take it anymore. And the atom actually splits and becomes smaller atoms. Breaks apart into smaller component atoms. We ourselves in atom smashers can do this to atoms. We can smash them apart. And radioactivity can happen anywhere in the universe. In addition, some of the atoms I've talked about that are made by stars are now inside the next generation of stars. And when they are ready to make an even heavier element, those elements, like let's say oxygen, could then be an oxygen from a previous exploding star, could be inside a massive star, and then when its oxygen's turn to be made into heavier things, that old oxygen atom could be converted to silicon, and the next step and the next step. So no one guarantees an atom forever existence. If you get under the right circumstances, you could be made into different elements.
Given what you said about black holes, are we at risk?
Are we at risk about black holes? So I have really good news about our, remember location, location, location. Where black holes have the most food and where giant monster black holes tend to form is the centers of galaxies. In the middle of the Milky Way, for example, there's a black hole that's already eaten 4 million suns. But the centers of galaxies are where they preferentially occur. We are in the suburbs of the Milky Way galaxy. We are far from the center. We're sort of in the Redwood City, Los Altos area of the galaxy. So all the stuff that happens that Mayor Breed is complaining about doesn't happen to us. We're in the suburbs. So anyway, so our location is such a good location that there doesn't seem to be any kind of hungry black hole nearby, and I'm not worrying about that when I can't sleep at night. Black holes are elsewhere.
What did the Big Bang create? Our solar system, the Milky Way, or something more? And what preceded the Big Bang? What created the Big Bang?
Yeah.
And is the universe constantly expanding so that eventually it will die?
Great. When I was in graduate school and I started teaching, one of the things I asked my professor is, my God, you know, I know a lot from graduate studies, but what if the class asks you a question that you don't know the answer to? And I had a really great professor. He said, don't worry, just praise the question. If you praise the question enough, they'll forget that you didn't answer it. So that was a terrific question. Really, and you looked so prepared when you asked that question. I just want to congratulate you on that. So, of course, I'm joking. This is not a question you can answer in 30 seconds. I already ignored the previous time someone asked that question. But so let's say a little bit about the Big Bang. The Big Bang was actually a put down. The word Big Bang was created by Fred Hoyle on the BBC. Fred Hoyle had his own theory of the origin of the universe, hated the Big Bang theory. So when he was in the 50s asked to give a big discussion about the universe on the BBC, he tried to come up with the most sarcastic description of the theory he hated that he could possibly come up with. And he said in his British accent, oh, that theory of the Big Bang. And he was so upset when the people whose theory was said, oh, we've been looking for a name. That's great. Thank you, Fred. We'll call it the Big Bang Theory from now on. So the Big Bang Theory says that the universe began with a giant explosion. When I talk about supernova explosions, many people are reminded of the Big Bang explosion. But the Big Bang explosion was very different. The supernova is an explosion of a star in space. The star and the space already exist. The star just becomes unstable and explodes. The Big Bang was very different from that. The Big Bang was an explosion of space, of time, of matter, of energy. It was the explosion that made the universe as we know it. Space, time, matter, and energy were created in the Big Bang. So since time didn't exist until the Big Bang, asking a question what was before the Big Bang has no meaning. The great religious thinker St. Augustine during the Middle Ages was asked by one of his acolytes, great father, I have a question I've never been able to answer. What was God doing before God created the heavens and the earth? And supposedly St. Augustine went away and thought about it and came back and said, my son, God was making hell for people who ask questions like this. So none of us can answer what happened before the Big Bang. There are, of course, theories, multi-dimensional, 11-dimensional quantum mechanical foam out of which we popped, but those are just angels dancing on the head of a pin kind of theoretical ideas. For astronomers who rely on experiments, the Big Bang is the beginning of everything, and it now looks like the Big Bang will continue forever. Not only that, it's actually speeding up, which is, again, a topic for another lecture. But it does look like the Big Bang was the beginning, and there doesn't seem to be an immediate end in store.
Okay, I guess
Well,
I've got the mic here. Thank
Let's
you for making this so much.
Let's do one more question, and then I'm going to let people look like they're kind of ready to go home. And so if you have more burning questions, you can come up afterwards.
I've got the mic.
Yeah.
Thank you for making this so much fun. So my question might actually extend that last question. You talked about electrons and protons being there in the beginning. Was that there before the Big Bang, or did the Big Bang create that? We've heard also about what makes up protons. There's even smaller particles. We've also heard about dark matter. And I'm wondering whether that plays any part in this or doesn't. But I'm going to go back to your first thing about you saying there was only hydrogen in the beginning. And so my question is, where was that in relation to the Big Bang? Was it there before the Big Bang, after the Big Bang? And could you talk a little bit more about the first simplest particle that was there?
Wow. You guys are good. Have you seen how they snuck in just about every part of an astronomy textbook into the questions? That's good. She even got dark matter. This is a good group. I'm impressed. As I said, I can't answer any questions about before the Big Bang. There's no before. Time begins with the Big Bang. Now, if you think that's a religious kind of distinction, well, we are in a church. What can I tell you? But that's the experimental distinction. I cannot talk about time or anything else about which we cannot do experiments, about which we can't do observations. We can theorize. Some people associate God with the Big Bang, and that's perfectly fine if you want to do that. Some people associate quantum mechanical 11-dimensional foam, and it's fine if you want to do that. But for an experimental scientist, everything begins with the Big Bang. And the Big Bang was very, very hot, so at the beginning, things were so hot, so violent, and so energetic that even protons probably didn't exist. The subparticles of protons, which we now call quarks, were probably there. Was probably a quark soup mixed with electrons and enormous amounts of energy. Great photons of gamma rays were probably the dominant part of the universe. Out of that, eventually, as the universe expanded, things cooled. And as things cooled, the quarks joined and became protons and neutrons. The electrons at first were all over the map, but eventually they found the protons attractive and got together with them, and regular matter began to form. So ultimately, we owe the existence of matter as we know it to the cooling caused by the expansion of the universe. As the universe expands, it gets cooler and cooler. Now, as we astronomers like to say, the universe is real cool. And as a result of that, stars could begin to shine. For a while, the universe was hotter than stars, but then stars could form out of regular matter, stars could begin to shine, planets could form, new matter could come out of supernova explosions, and the universe as we know it was formed. So let me end there by saying that I do have a website where people can go if you want to read more about some of these topics and learn where you can get great astronomy pictures and things like that. I also have a mailing list for really nerdy people who are interested in being on the mailing list for future lectures. I put those on the piano if you want to come up and sign up for it. And otherwise, let me just thank you for your cosmic attention. I appreciate it.